position of the microphone.
Yeah, that could be the case as well. So we in the next talk is going to be about machine learning based 3D track trigger for Belle 2 by Sebastian Skambraks, if I pronounce that correctly.
Yes.
You have
right.
15 minutes, if I'm not mistaken, and you can start if you want.
25, I think. Is it 15?
Yeah, yeah. I mean, I should pay more attention. Yes, you're absolutely
okay,
right.
25. Yeah. Otherwise, I have to rush. When you can see my slides.
Yeah, that looks
okay. Then I start. Okay, I'm Sebastian Skambraks from the Max Planck Institute in Munich, and I will present you the machine learning-based 3D track trigger we are developing for Belle 2. The main component is the neural network trigger that I will introduce, and then I will show you a 3D HUF finder that we develop as an improved pre-processing for this neural network trigger, and show you some results with simulated initial state radiation events and with early Belle 2 data. Okay, so this is planned at Belle 2. And Belle 2 is the new detector at Super CAG-B, the asymmetric E+, E- collider operating at the Y4S resonance. The plan with Super CAG-B is to achieve 40 times the luminosity of the predecessor CAG-B, and right now almost the same luminosity as in the predecessor experiment is reached. In a typical Y4S event, we have about 11 tracks per event, and the typical transverse momentum is 500 MeV. So this is how Belle 2 looks, and surrounding the collision point here. And the third detector and the main tracking device is the central drift chamber, which consists of 56 layers of sense wires, which are closely parallel to the beam line. And with this track trigger at the first trigger level, we like to suppress background tracks. So all tracks not pointing to the collision point where the physics is expected, this is background, and we like to identify it at the trigger level to suppress it before recording. The background processes are expected to increase with the luminosities, therefore we expect heavy background conditions. The main processes are the Tuschek effect, this is inner beam scattering, backscatters from radiative barbars, and beam gas events. And with the neural network trigger, we like to reject the tracks not pointing to the IP. And this has to be fast in a very short latency of under 1 microsecond, so it can be used for the first trigger level. And this plot on the right shows early Belle 2 data, where the luminosity is still very low, but you can already see the huge peaks here outside. And with the Z-vertex trigger, we could make such a cut, for example, here at ±20 centimeter and get rid of most of this background. So here's more details on the track trigger. So there's several, the CDC is the only track trigger. There are other detectors used, but they cannot be used for tracking at the first trigger level. And the maximum latency of the first level trigger is 30 kilohertz, and the total, the trigger rate is 30 kilohertz, and the latency is 5 microseconds. And the CDC trigger pipeline is illustrated here on the right. There we have at first a track segment finder, which is the first noise suppression and data reduction step. This is followed by a track finder based on a HUF transformation, presently a 2D HUF transformation, and then follow the precise single track reconstruction methods, including the neural network. In the central drift chamber, we have the 56 layers of sense wires, and they are arranged in 9 so-called super layers of wires with the same orientation. This is either axial super layers, which are parallel to the Z-axis, and inclined stereo layers, which have a twist with respect to the Z-axis with a different stereo layers shown here in this table. And the first step in the trigger is then finding track segments in each super layer. This means to look for this hourglass-shaped pattern here, and if at least 4 out of 5 of the wires within such a pattern have a hit, the track segment is said to be hit. And the output of the track segment finder is then just a single wire. If the central one is hit, it's the central wire. otherwise one of the two wires above. And additionally, we have then the drift time with respect to this wire, which is a good distance measure between the track and the wire and can be used for track reconstruction. So here's at first on the right an illustration of this drift time to distance relation, and there you can see it's this is the distance, this is time, and this is approximately linear. So it can be used as a distance measure. And on the left, this will be an event display like this. Here you see in red the hits from an Y4S event. And there you can already see by eye the tracks. And if you add noise, the picture gets more fuzzy. But after running the track segment finder, you can see that most of the track segments are only found along the path of this Y4S tracks, and only very, very rare tracks are pure track segments or pure background track segments. Okay, and this is then used as input for the neural network together with the estimates from the HUF finder. The neural network is a robust function approximator which allows massively parallel processing and is well suited for implementation on FPGAs. And with this neural network, we process maximally one track segment hit per superlayer per track. So it's for single track estimation, and each of these track segments is encoded with 3 values. Well, I will explain them on the next slide. It's 2 for the position information and the drift time. The output value of this neural network is just simply the scaled z and theta values, so the 3D track parameters of the single tracks that should be processed. And yes, so now to the input representation. This is done in a pre-processing step for the neural network. There at first, for the 2D tracks, which are found only based on the axial hits, the stereo hits are matched to these 2D tracks. And then the position information of these track segments is encoded relative to the found 2D track. This is phi rel is then the distance between the track segment position and the 2D track. So this phi distance here. And alpha is the path length, the arc length along the 2D track to a track segment divided by the radius of the 2D track. So it's like a 2D coordinate system relative to the 2D track. And additionally, the drift time as third parameter. We have a setup with expert networks for missing hits. So for missing stereo hits, with 4 stereo superlayers, we have therefore 5 networks in total, 1 network when all stereo hits are present, and for each stereo layer missing, a dedicated expert network. This setup is already implemented at Belle 2 and running in the present runs and recorded. The data is recorded, and we are debugging the data coming from the network and making first performance studies. On the right, you can see such a plot. There are still errors, but if we do error correction in software of the errors we have already found, we can see that we achieve a resolution of the order of 4 centimeter with this network. Okay, then let's come to the 3D HUF finder. So the idea of a 3D HUF finder is to include the stereo hits in the track segment. The stereo track segments for the track finding, and this improves the track finding efficiency and allows possibly to get the hit selection of axials and stereos in a single step, so they don't have to be matched afterwards in the pre-processing of the neural network. The method we use is based on a Bayesian parameter estimation. So we estimate a set of tracks given a set of hits. And in the setup, this structure here is represented as a bin data structure that we store as pre-trained patterns in the data. And this is a very general approach. By changing the track and hit parameterization, we could simply change the model or adjust it to different conditions. but the results are equivalent to a Hough transformation, which I'll show in the next slides. So this is now the basic 2D Hough transformation. Thereafter a conformal mapping, we can represent the hits in assigned curves in the track parameter space. So this is then a single hit. If you have several hits, and then you find as the intersection point the track parameters of the track that has caused these hits. The blue band I've shown here is tracks larger than 350 MeV. This is the region that can be found by the present 2D finder. So if we now do this in a binned parameter space, we can do nearly the same thing, but we for the track finding we use a clustering algorithm instead of analytically searching for the intersection points. And yeah, we can find the tracks with this clustering algorithm. So now to include the stereo hits, the problem is the axial hits already are points in the single points in the transverse plane, while the stereo hits, they appear as line segments. But if we now use theta binning, we can find such single point representations of the stereo hits as well. And this allows us to construct such a 3D Hough plane stacked out of 2D Hough planes. This is now including the axial and the stereo hits. And here on the right, you see this is the correct theta bin, let's say, and there all the track segments curves intersect in a single point. If we go to a wrong or displaced theta position, you see that only the axials intersect in a single point, but the stereos have their intersection point to the right and to the left. And yeah, now more details on the setup of this 3D finder. We represent the structure P of T track given a hit as a 5-dimensional array with 3 dimensions for the track phase space. This is inverse PT, phi, and theta, and 2 for the hit phase space. This is the ID of a track segment and the position of the priority wire. This can either be the central one or one of the 2 wires above. And this 5-dimensional array is then trained using Monte Carlo data. And yeah, this I will show you here on the next slide. So in the training, we have the first step is like filling a 5-dimensional histogram where we look up the track to hit relations for each track in the training data set. And after this array is filled, it's normalized such that all tracks are equally probable. And in the end, a bit width is applied. Currently, we use 3 bits, which this is to make it possible to realize this on hardware at some point. And this means such a single hit, the maximum weight of a single pixel here is 7 with 3 bits. And this could be adjusted, but yeah, right now it's 7 hits. No, 3 bits maximum weight contribution is 7. So after creating the Hough space by summing up all the single hit contributions, we use a clustering algorithm to find the peaks and the clusters. And in the software simulation right now, we have a density-based clustering algorithm, which uses 2 parameters. One is this min weight. This is 24. So each cell that is considered to be a member of a cluster must have at least 24 weight. This means at least more than 3 hits must have contributed to a single cell. And for clusters to be found, they must have at least 4 contributing hits. With these clustering parameters, the clusters are found. After they are found, the local region around the peak is selected for the track parameter estimation by requiring a minimum weight of the clusters in the vicinity of the peak. And there we require right now that the cluster cells in the Hough space must have at least 85% of the peak weight. And this local region around the cluster center yeah, there then we calculate the weighted mean to get the track parameters of the found 3D tracks. Okay, then I come to some efficiency studies. This is a simulated single track efficiency study with tracks displaced along the z-axis and with 4 different background types. And yeah, the background types are sorted here by the background level. But the first thing you can see is that it's quite robust, the method of for different background levels. There is a big difference between the 2D lines. This is the flat efficiency distribution here, and with the 3D finder distribution, which has this peak around the IP. And this is very beneficial because you find here you have a much larger track finding efficiency with the 3D finder at the IP. But if you go away from the IP, you already achieve background suppression at the track finding level, which is not possible with the 2D finder, of course, because it's only using the axial hits. So the efficiency of this 3D finder is quite good. Not all of the tracks can be processed by the neural network yet, because some of these tracks may have not enough stereo hits. But the right plot shows the total efficiency, so the efficiency of the track finder multiplied with the neural network efficiency, and here you see still an improvement with the 3D finder compared to the 2D finder, and also the background suppression for displaced tracks. Okay, then I come to initial state radiation events. This is a typical candidate of events with a low track multiplicity. And yeah, here you see simulated the pi plus, pi minus final state, a hadronic final state, and the measurement of such hadronic final states is quite important. For example, in the mu and G-2 experiment, to limit the theoretical error. And yeah, here you see 2 distributions for the transverse momentum and the polar angle. And you see especially here in the low PT region that the 3D finder, this is in orange, has a larger efficiency than the 2D finder, and the same is in the forward and backward region, where you have an improved efficiency with the 3D finder. In total, this makes yeah, about 1.5 times the efficiency of the existing 2D finder. At the same time, there is no loss of efficiency in the high PT region and in the central region. If we now build an event-based trigger using the neural network estimates, and we can also compare the 2D finder and the 3D finder. And now the event efficiency here means at least one of the tracks is found within the z-cut region of the neural network. So we take the estimate of the neural network and only take the event if the estimated track value is smaller than the cut value here on this axis. And for single track events, if we cut, for example, at 20 centimeters here, we get 85% of these initial state radiation events. And for 2-track events, we get even 98% of these pi plus, pi minus events. So we have, with the 3D finder, huge efficiency improvement, and yeah, since it's quite similar for the 2D finder and the 3D finder, we have no track loss, and the additional tracks found additionally by the 3D finder can be processed by the neural network. Okay, then I come here to the last plots with some real data from Belle 2, some very early data. And the green curve is the reconstructed tracks, and in orange and blue, again, the 3D finder in orange, the 2D finder in blue. And so, yeah, the finders are simulated using real data as input. And you see the same, similar efficiency improvement here now in the low PT region. And the same is true for the forward and backward region. And this corresponds to an efficiency improvement here for tracks from the IP. But what you can also see now in this distribution, because you have here these large tails of background tracks, that the 3D Finder can also suppress the background tracks displaced here from the IP. And yeah, this background suppression here has the result that the total number of tracks found by the 3D Finder in this example is smaller than with the 2D Finder, because it already suppresses parts of some part of the background tracks. Okay, then I come to my conclusion. With this, we have the neural network that we can use to build efficient Z-cut-based triggers, and which allows to relax the other trigger conditions. And we can especially rescue many low multiplicity events which would otherwise be lost, because we might, two-track triggers are already critical. Single-track triggers are, very difficult, I would say. But the neural network, it's working, but it requires pre-processing, hit selection, track finding, and the calculation of the inputs. And for this improved pre-processing, we are developing this 3D Finder. The neural network is already running in hardware. And in a debugging stage, the 3D Finder still has to be developed in hardware. But with the 3D Finder method, in principle, we see this 1.5 times improved track finding efficiency for tracks from the IP and the background suppression of the displaced tracks. Okay, this is my talk. So far, do you have questions?
Yeah, thanks very much for this very interesting talk. If people want to ask a question, please raise your hand. I was wondering, when you early on discussed the 2D and 3D Finder performance as a function of that, you had different backgrounds, but you didn't quite explain which backgrounds were taken into account and what their characteristics is.
Well, it's the general background mix that we expect at Belle 2, and it's the official background types that were used over the recent campaigns for background studies. Okay, I can go a little bit more into detail. We have, okay, red, this is no background. Then this is phase 2 background, so this corresponds to earlier, low luminosity conditions. This is just an older version of the background expectation at full luminosity, where that was a little bit incomplete, and there's a lower background level, and in total, it's just sorted around by the background level. This is no background and more background adding up.
Can I ask a follow-up question on that?
Sure.
This is Andy. So you have very low multiplicity events. So in my mind, you must be extremely sensitive to the modeling of the background, right?
Yes.
How confident are you that this is properly modeled in the simulation? Particular beam backgrounds?
Yeah, the beam backgrounds are, of course, problematic. We plan, as soon as we have collected background samples from real data, to confirm this with real data, with real recorded background as well. And this is the reason why I use many different of the official background campaigns, because you have some small changes and get completely different topologies of the background. But
so are you
has to be confirmed.
Taking some zero bias data and then using that? Because that would be the ideal situation for your training, right? And embedding into zero bias data that you practically have.
I don't know what you mean with zero bias data. We plan to use real data from the detector for the training of this method.
Yeah, but for background only, like basically a random trigger that takes background only events and embed your signal into this.
Yes, this is what we like to have as perfect background simulation. But in the end, for the training of the neural network, we are of course more interested in the efficiency for the signal and not in the efficiency for the background track. The background tracks have to be suppressed, and we want to save all the signals. So yeah, it's always a trade-off.
Okay, I saw another hand raised.
It was me, Marcus Salva. I had a similar question, and I was also curious about when you show the set of all the tracks that you reconstructed. So you said you want the tracks around 0, but what are the other?
I didn't hear the end of the question.
Me
Did you
neither.
mean what?
Yeah, what are the other contributions? What are the things at plus 50, minus 50?
You broke up in the middle of your question. I think you have to repeat. Sorry for this.
Okay. Well, this is real data here from the detector, and you see collisions we have here at z equals 0, and the rest corresponds to some beam background events. This is all background created by Belle 2 that needs to be cut off by such a 3D track trigger.
So that's the bunch spacing.
This is not the bunch spacing. This is particles lost from the beamline, or maybe backscatters from radiative Barber events. This is a huge contribution. I guess most of them is backscatters from radiative Barbers.
Okay. All right,
and
thanks.
then, yeah, we have particle loss from the Tuschek effect and from beam-gas interactions. And they just hit the beam pipe anywhere and create random tracks.
Okay, thanks.
Okay, I see no more questions. I presume that Andy didn't lower his hand, or do you have a follow-up question, Andy? Doesn't seem to be the case. So thanks very much again for this nice talk. If you could unshare your slides and